Windows likes to refer to them as folders. Think of them as directories, okay? So directories are just groupings of files which themselves are just collections of bits, all right? You have an operating system. What is an operating system? Well, an operating system is a program, right? It's software, if you will. It's a program that does various things. And one of the things that it does, there you go. One of the things that it does is it controls the file system. So it has this so part of the operating system is known as the file system, and it manages your files. So it knows how to write to the files. It knows how to read from the files. It knows how to store files, right? And it also understands this organization, this understanding of directories, how you can have a directory inside of a directory, and you can have other files also stored in directories, right? Now let's dive in. Now, I'm guessing most of you knew everything I just said, right? But now let's actually dive in. Let's consider the word interface. What is an interface? Well, we have a file system, which is great, but we need to interact with the file system, right? Having files on a computer is useless if you can't access the files. You need to be able to read them, you need to be able to make new files, you need to be able to delete old ones, you need to be able to search across them, right? You need access to your file system. An interface is a medium between two entities, the user and the actual system that you're trying to use. The interface sits in between. Think of it this way. Consider your car, or a car. The pedal is the interface. It's the medium between you and a lot of things that are happening underneath the hood. The engine, all the pistons, all the mechanical stuff. You control that with the pedal. The pedal is the interface. It's the medium by which you can communicate with that complicated system underneath the hood. Consider this, though. When driving a car, you don't have to know all that complexity that's underneath the hood. You don't have to know about pistons and the engine and oil and a lot of that stuff. All you have to do is know how to press the gas pedal correctly, right? And maybe turn the wheel. You don't have to understand the complexity that lies inside the car. That complexity is hidden from you. It's abstracted away. Remember this word, abstraction. Abstraction means hiding, not showing you. It's none of your business. You can always open the hood and look inside if you choose to. But if you don't care, you don't have to. You're simply a user of all of that. And you use it simply by using this and this. You don't have to worry about that. Does that make sense? Well, with a file system, we have a similar thing. This here might seem familiar to you. This is an interface. It's known as a file browser. Why? Because it allows you to browse files. Browse the files in your file system, right? So you have access to if you're on Windows, to your C drive, which is kind of your root. It's like the biggest directory. It's the highest directory. Underneath that, you can then have more files and directories and so on, so you have this sort of tree structure. This is an interface. You don't know all the things that are happening underneath the hood. All of the code that manages your files, that writes files, this is really weird, sorry. All the code that manages your files, the operating system code, the file management, all of that stuff is abstracted away. You don't know, you don't care. All you care about is that you can see the files, you can click on them, you can open them, you can browse them, you can delete them. It's like using the pedal. This is your interface. Who are you? Well, you're a user, right? You are a user of the system. You are the user of the interface. Yes? This is called a user interface. You see where the words are coming from. Now notice how there are graphics here. You can see pictures. These icons, these folders, this text, right? There are pictures here. You can see them. There are graphics here, right? This is known as a graphical user interface, also known as a GUI. If you've ever heard of that term, GUI, you now understand where that comes from. A GUI is a graphical user interface, that is to say, a medium through which you can interact with some sort of a program, some sort of a system. Make sense? Okay. Well, it turns out that a graphical user interface is not the only kind of interface. You can have something like this. This is sometimes called a terminal, also known as a command line interface. What is a command line interface? It's actually very similar to this, except instead of graphics, instead of clicking on pictures and dragging them around and doing stuff like that, you're typing in commands. But at the end of the day, the purpose is the same. It's an interface. It's a mechanism through which you can interact with something behind it that you do not see, the actual programs underneath. Okay? So this is an interface and that's an interface, but this is a graphical user interface and this is a command line interface. There are other kinds of interfaces as well. Suppose you write a program. You're actually writing code. This might sound abstract to you, but it won't be too difficult. You're writing some code, and then somebody else wrote code. They wrote a whole bunch of really complicated code. You want to now use their code. What do you suppose you need to use their code? Some sort of a medium, something in between that will help you interact with all of that stuff that they built. An interface, okay? But when you're programming, it's a different kind of interface. It's a programming interface. It's still a medium through which you're communicating with the system. But now you're doing it by programming, not by clicking. So this is a programming interface. Now it just so happens that just calling it a programming interface wasn't enough, so engineers started calling it application programming interface, also known as an API. So now you know where that comes from. So an API, or an application programming interface, is the medium. It's that thing in between. It's the pedal, if you will, that you programmatically use to communicate with a system. Got it? Simple, right? Very cool. All right. So as you accumulate, so we understand how data is stored, zeros and ones. We understand that data on the computer is data on the computer is organized into these groups called files, and that files can be further organized into these categories, these directories, which Windows, of course, refers to as folders. Same thing. Suppose you have a lot of that. Suppose you have a whole bunch of bits. So many, in fact, that it doesn't fit on one computer. Well, what can you do? Well, you can just go and buy more memory, right? So you can add more memory to your computer. This is known as vertical scaling. Scaling means making it bigger, right? Scaling, okay? So you're vertically scaling. You're adding more stuff to your computer, making your computer more powerful, thereby scaling your computer. The problem, though, is at some point, scaling your computer becomes very expensive and actually almost impossible. So what you can do, though, instead of making one computer really powerful and really buying supercomputers and so on, you can instead just buy a bunch of computers and stick them together. This is known as horizontal scaling, okay? So making one computer more powerful is vertical scaling. Adding computers is horizontal scaling. Make sense? Good. So we talked about a file system. So a file system, okay, it's the place where a whole bunch of files are stored. Makes sense, file system, system of files. Okay, and directories, which are just categories. But what happens if you have so many files that they don't fit on one computer? Well, as I said, you can add more computers and basically distribute the files across the computers. That is to say, take some of the files, put them on one computer, take some of the files, put them on another computer, and so on and so forth, but treat the whole thing like one virtual file system. That is to say, when you're a user, you're using it, you don't really know what computer it's stored on. You just say, I want that one, and it just goes to that computer, brings it to you, and shows it to you. Got it? Okay. There are different distributed file systems out there. One of the really popular ones is known as the Hadoop file system, okay? Hadoop Distributed File System, HDFS. Okay. If you guys have heard of Hadoop, raise your hands if you've heard of Hadoop. Oh, not too many. Wow, that's surprising. Okay. Hadoop is very popular. Well, it was even more popular a few years ago. So Hadoop basically has two parts. One is the distributed file system, and one is a thing called MapReduce, which allows you to compute over the data. But don't worry about that for now. For now, just know that Hadoop allows you to create a distributed file system. Again, it allows you to scale horizontally. Cool? Okay. Data, which can be stored on files, comes in two flavors, typically. It comes in a structured form, and it comes in an unstructured form. And what do I mean by this? This is some text about Charles, right? So it talks about him, where he was born, etc. This is text. This is things that you as humans can read and understand information about Charles, right? This is, though, an example of unstructured text. Why is it unstructured? Notice the things that are found in this text. So in this text, we have information like his first name, his last name, where he was born. Now, these are things that you can kind of understand because you speak the language, right? And you know how to read, and you know how to reason, and you understand how to stick words together, and it's making sense to you. For computers to understand that is actually very difficult. There's actually a whole branch of computer science known as NLP, natural language processing, which attempts to do exactly this. It attempts to take natural language that you and I understand, and make sense of it, understand what's in there, what it's about, etc. That's called NLP. Don't worry about that for now. So this is unstructured text. It's just information, but there's no structure to it. It's not labeled. I don't know that this is his first name. I don't know that this is his last name. I don't know what that is. Okay? It's just a bunch of text. Conversely, this is an example of structured text. So this is a structured data. This is a CSV file. If you've ever seen a file with a .csv at the end, CSV means comma separated values. CSV. It's basically a table. Okay? So it's a table where you have columns, kind of like what you see in Excel. Kind of like what you see in Excel, right? You have your columns. And each column has a label at the top, right? So in this case, the label here is ID, and you have a bunch of IDs. First name, and a bunch of first names. Last name, a bunch of last names. For any piece of data, I know what it is, right? This is an example of structured data, okay? The data has structure. Every piece of the data is labeled, so I know what everything is. One example of this kind of a file is a CSV file. By the way, you can open a CSV file in your Excel application. It will open it. So anything .csv means comma separated values. Why comma separated? Because that's what it looks like. It's literally like a value, comma, value, comma, value, comma. And then you end of line to go to the next row. Value, comma, value, comma, dot, 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 dot. We all know what CSV is? Cool. Here's another example of a structured file. This is XML. Again, note that it has these sort of tags. Raise your hand if you know HTML. Okay, so a lot of you already did the homework or you knew from before. Happy to see it. Okay, for those of you who didn't, basically these things here are referred to as tags. Okay? XML is not exactly HTML, but they're similar enough that if you know it, this makes sense to you. This tag basically says what is inside. So in this case, first name, that's the beginning, that's the last name, and the stuff in between is what it is. So in this case, Avetik is the first name. Isaakian is the last name, etc., etc. And that information is about a person, and all of this is about people. Fair? Okay. You can see that this has structure, right? For anything, if I point at any piece of data, I know, I can see exactly what that piece of data is. The data is labeled. It has structure. This, at this point, is probably the most popular form of storing structured data. It's called JSON. This is actually a sort of a piece of JavaScript. It's a sort of a subset of JavaScript. And you will learn JavaScript soon, so don't worry. But basically, this says exactly the same thing as what XML did. So if you understand this, this is the same thing. It's just stored in a different format, right? The way you store it is a little different, but the idea is the same. So you have people, that's a list basically. This is just a container, an object, if you will, which says, you know, first name is this, last name is that, birthday is that, right? So again, every piece of data has the label, so you know what it is. It has structure, okay? Cool. Okay, let's consider a use case. So you guys are running a store, right? So you buy a store and you have lots of customers, lots of products, lots of things. You need to manage all of this information. What was sold? How many items were sold? Who bought this information? These products. Which customer? Perhaps that will allow you to make smarter marketing strategies, right? If you keep track of who's buying what. So what we could do, remember CSV? Remember this idea that we can store data in tables? Well, imagine that's what we're doing. Except instead of just having one table, consider that we have one table about customers. Okay, so we have a column about the customer ID, first name, and last name. We have another table about products. Again, the product ID, the name of the product, and how much it costs. And let's just say this is in dollars, just whatever. Okay, then we have purchases. Interesting. So what this means is that this is the purchase ID. This is the customer ID. So that's number 2. So that's Shiraz, right? So what this is saying is that Shiraz purchased product number 1, that's pen, 3 of them. So what this is saying is that Shiraz purchased a pen, 3 of them, right? What does this say? This is just an ID of the purchase. Who is this? Charens. So Charens bought which product? Again, a pen. How many of them? Palm. Make sense? Now note something interesting here. That even though these are separate tables, the tables can refer to each other using an ID. So in this case, for example, this number 2 refers to Shiraz, which is in a completely different table, by Shiraz's ID, right? So there's a relationship being created across tables. From one table, you have a relationship to the other table. Relational. You might have heard of these databases called relational databases. Now, we'll talk about those later. This is an example of a relational database. Okay, so we'll see some examples, but relational databases work exactly like this. You have tables, and you have relationships, these references by ID between the various tables. Okay, so if you've heard of SQL or MySQL or SQL Server, all these fancy things, these are all relational databases, and all of them, at the end of the day, basically store a bunch of tables that refer to each other, that have relationships between them. Now, this is just showing what you already know, that we have relationships. What I was just saying. So relational databases, some of the most popular ones that you will hear. If you ever hear anything with the word SQL in it, it's a relational database. It's a database that has these tables with relationships in between, right? So MySQL is the really popular one. Postgres, very popular. And then slightly maybe less popular, Oracle and SQL Server. These two are open source, which is why they're used very often. Open source means literally the code is available. You can look at it, you can hack it, you can use it without a problem, without paying anybody. For these, you have to pay to use. The difference. Cool? So now if anyone tells you I'm using a database, a relational database, yeah, which kind? Which, is it MySQL? Yeah, how do you know? I went to class. Okay, cool. All right. So what is SQL? So these 3 letters keep coming up, right? SQL. It stands for Structured Query Language. Language. Interesting. Why do we have languages? What is a language for? Communication. Exactly. A language, I'm speaking English, communicating with you so you can understand. What do you suppose this language is for? To communicate with the database. Exactly. This is a language that allows you to communicate with relational databases. Okay? So if you think about it, a relational database, as we discussed, stores data. Okay? It stores data in tables. Fine. It has these tables can have or rows within tables can have relationships between them. Hence, relational database. Okay. But how do I now search that database? Right? How do I actually interact with that database? I need something, some language to talk to the database, basically, right? So SQL, structured query language. Query means like asking question, right? You're querying it here. Language, obviously, structured because there's structure to it and because the data is structured, right? Okay, so we have SQL, and here's an example of an SQL query. Look how scary it is. You're not scared? No? Okay. Okay. So there it is. Can the people in the back see the text? Can you read it? You want me to zoom in or it's okay? Okay, John. Okay. So this is just a reminder of what our tables look like. And this is the query. Let's sort of mentally understand what this query wants from the database. What is it asking? Okay. So first, let's focus on the from clause. The from clause says the tables that we are interested in. Why? Well, a database can have lots of tables. You might, yes, we have these three, but you could have lots of other tables. You can have tables about your employees, for example. You could have tables about, I don't know, meat products, I don't know, cashiers, how much each employee makes. You can have lots of other tables, right? Information that is not relevant to the question that we're asking. So what we do is we limit the query to say, I only care about these tables. So that's what the from clause says. So the from clause says, only use these three tables, forget about the other tables. By the way, you can almost think of tables like, for those of you who used Excel, you know you can make a spreadsheet, but then you can add another one, and then you can add another one. And imagine each one of those spreadsheets as a table, and you can refer to things across spreadsheets using an ID. You can almost think of it that way, just mentally, so you understand what we're talking about. Okay, so this says what tables we care about. Let's consider the where clause. This is interesting. So the where clause says, go to the purchase table, that's this guy, and get its customer value. That would be this column here. And it's saying, have that be equal to the customer ID. That's this one here. This is known as a join. It's saying stick the rows that have this ID with that ID. Line them up. Remember, we have two separate tables, but the IDs are going to line up. It's saying, and also, furthermore, take the product ID, that's this guy, and stick it, match it, line it up with the ID of the product table. Okay, so line that up. So we've lined this up and we lined that up. It's then saying now group by customer ID. So the rows that you've created by lining these things up, chop them up based on the customer ID. So if the customer purchased 5 products, you're going to get 5 rows for that, just for that one customer. Then what we're saying is we're going to select. Select is the part we're going to get from as a result. We're going to get the customer ID, and then for each customer ID, we're going to get the purchase quantity, that's this, multiplied by the price of the product that they purchased. Okay? Then we're going to add them up. So the result of this is that for every customer, we will know how much money they spent at our store. Sort of makes sense? Don't worry, this is not going to be on the test. I just want you to understand what's happening with databases, okay? This is a survey. Don't worry, I'm not going to, just understand it for yourself, okay? It makes kind of sense? Good. And by the way, this is what I would get as a result. So the customer IDs would be these, 1, 2, 3, right? Because those are our customers. And these would be the result of all the money that they spent. So here you can see that number one, that would be Charens, is the big spender. He's the one that's spending most money at our store. And the person who's spending the least, wait, sorry, number three, I'm sorry. Number three is the one, Avetiki Saakyan is the big spender. He spent 27 bucks, right? Way more than the other guys, okay? Make sense? Cool. Okay, so we talked about relational databases, right? These databases that support SQL, the understanding of a structured query language, a language through which you can communicate with the database. There are no SQL databases. These are databases that don't follow these rules. Some of the databases may not store tables. If you recall, we studied different structures. We studied tables, that was the CSV example. We studied XML. We studied JSON, right? We saw those examples. Well, it turns out MongoDB, for example, is a database that stores JSON. Bison, it stores it in binary, but no one cares. It's JSON. It stores JSON, right? It's a database that knows how to store JSON documents. There are databases that know how to store XML documents. There are databases that know how to store data as graphs, directed graphs, right? So storing data as tables is not the only way to do it. You can structure your data in different ways, and different databases do that. However, if you store your data as JSON, you can no longer use SQL because SQL by definition relies on this tabular structure, this relational form, which doesn't necessarily fit with JSON. So MongoDB has a different query language. CouchDB has a different way of querying. Neo4j has a different language for querying its data, right? So the query language has to match with the database you're using. Cool? Okay, good. Okay, you can structure your data in different ways. First of all, you can decide to store it as a table or as JSON or as, which is like a tree, or as XML or whatever. You can also, well, the naming of the attributes, right? Is it first name, or is it first underscore name, or is it just F name, right? Should I store the email in a list, or do I just assume I only have one email address? Understanding the structure of your data, deciding on the structure of your data, is called data modeling. You're modeling your data. You're trying to understand the structure that your data will have. Is this okay? Do you have questions so far? Have you missed anything? Yeah? It's like blank faces. Okay, no problem. Okay, so we understand that we can store data. We talked about file systems and bits and all that stuff. But at some point, we want to actually do something, right? We need to compute, okay? We need to have the computer actually do some calculations for us. It does this by using something like this. This is called a computation and processing unit, or CPU. It's your processor, okay? Your processor is basically a really complicated calculator. It knows how to do a lot of math, effectively. It knows how to load data and then compute over it, do mathematical things over that. Programs are actually just code that are stored just like any other piece of data on your file system, okay? So just like you have your JPG for your images and you have your whatever, name something else you have, DOC for your documents or TXT for your text files, you also have .cpp for C++ code. You have .java for Java code. You have .js for JavaScript code. All of the programs that you guys are using are just data, just like any other data. It's just bits stored on your file system in files, okay? This is an example of machine code. So this is the kind of code that your processor understands. It only understands basically Boolean logic, zeros and ones, yes or no, okay? There are some letters in here, that's because it's using hex, don't worry about that, just assume it's zeros and ones at the end of the day. But this is machine code, and it does something. Can anyone tell me what this does? Exactly. Okay, believe it or not, people used to actually program computers like this. They used punch cards. So what they would do is there would be a computer, and they would have these cards. And on the card, you would punch a hole. And if you punch a hole, it means a 1. If you don't punch a hole, it means a 0. And they would go, chick, 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 chick. Ah, crap, throw it away. Next one. Chick, chick, chick. And then have a whole bunch of these cards, feed them into the computer. Don't drop the cards. Okay, feed them into the computer, and the computer would read the holes and know 0, 1, 1, ba, 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 and in that way execute the program. So people literally programmed like this. Then engineers began to realize, okay, we can do something smarter. And so they came up with a different language, or a class of languages called assembly. This looks a little bit better, right? Definitely better than the previous example. This is an example of assembly code that then can be compiled into, translated into machine code. Okay? So you have a program called a compiler, which knows how to take this as input and then turn that, translate that into the machine code, which is the output. So you write code here, you compile it into machine code, then you give it to your processor, and your processor runs and does, and then you have Facebook. Okay? Can anyone tell me what this does? Not bad, yeah. It was a good guess. I'm guessing you saw Hello World and yeah, it prints. Okay, this is way easier, right? This is a language above assembly. These are known as high-level programs, right? So these are programs that are even simpler than assembly. This is an example of program written in C++, right? So this is C++ code. I don't expect you to understand it, but just looking at it, you can kind of figure out, okay, this is probably text. It has the word hello world in it. Cout, if I were to tell you, it's like a print. It will run and it will print hello world. Even if you don't understand the syntax, you don't know what int is, or that's a function and that's a library, you don't know any of that, intuitively you understand that this is way easier than that, and oh my god, easier than this, right? Again, this though requires a compiler, some sort of a program that can take this as input and turn it eventually into machine code that can be executed on your CPU, on your processor. With me? Mm-hmm. Okay. Okay, so we understand what programs are. They're basically a set of instructions, okay? You're telling the computer, do this, do that, do that, do that. You're communicating with the program. To communicate with something or someone, you need a language. We saw SQL, a language for communicating with a database, which is a program. This is some code, coffee cup.drink, work task executed. If the coffee cup is empty, you know, make coffee, refill, whatever. You understand? It's a stupid algorithm. But you get the idea. An algorithm is just a series of steps. We discussed this last time, right? So a program is just a language by which you can describe series of steps to the computer. You typically describe it, and in this class we will be describing it in a high language, in a high order language, that can then eventually turn into zeros and ones and run on the processor. So we will be using JavaScript to tell the computer what to do. JavaScript will then, at runtime, when it's executing, turn into zeros and ones and run on your computer or your processor, and then you will see the outcome of your application. Cool? Okay. Some theory. Raise your hand if you know who Alan Turing is. All right, some of you know who the father of what you're majoring is. So he's the father of computer science. If you're majoring in computer science, you probably should know who he is. He did lots of really cool things. One of them is he was thinking about a very simple problem. Well, intuitively simple. He was trying to understand what is computable. If you think about it, it's actually not that simple. What can you compute? That is to say, if you built like the most powerful computer in the world, what are your limits? Like, what can you do with that, and what can you not do with that? No matter if you have 10,000 of the best computers in the world, there has to be a limit to what it can do. What is that limit? How do we determine what is computable, what it can compute? And so he thought about this, and he came up with a conceptual model, a conceptual understanding of this machine. He called it, well, I don't know if he called it, but it's known as the Turing machine, okay? A Turing machine is basically this. It has an infinite tape on both sides, okay? So you just have a whole long tape going that way and a long tape going that way. And you have a head. And the tape can sort of slide underneath the head, going that way or going that way. Okay? The head knows how to do a few very basic operations. It knows how to read what's on the tape. Or the tape is divided into parts, so as you go to the next part, go to the next part. You kind of see what I'm saying? Okay, the head knows how to read what's on the tape, and it knows how to write something to the tape, and it knows how to go either left or right. That is basically all this machine can do. And what you can do then is give it instructions like write something, go right, write something. If that something is this, go left, blah, 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 right? Very basic instructions. That's it. It's the simplest thing you can imagine. And any computer that has ever been built, the most powerful computers that we have in the world, can't do anything more than this. The Turing machine literally says, this is, if you can write a program that runs on a Turing machine, then you can build a computer that does it. But if you can't do it on a Turing machine, you cannot build a computer that can do that, because it's not computable. Okay? Now, you can build computers that will do it faster, more efficiently, whatever. That's not what I'm talking about. I'm saying, can you do it? Can you compute the answer, or can you not? If you can do it on a Turing machine, then only then can you build a computer. If you cannot do it on a Turing machine, you cannot. We have a set of programming languages, as we discussed. Programming language is, again, a language through which you communicate with the computer. Well, what is a programming language? It's a set of instructions. You're telling the computer what to do, right? So you're doing computation. All of that turns into zeros and ones, runs on the processor, you're computing. It turns out that there are a set of programming languages that are known as Turing complete. A Turing complete programming language is a language that can do everything that you can do on a Turing machine. If you can program it on the Turing machine, you can program it using that programming language. There are languages that are not Turing complete. An example, HTML. It's a language, right? HTML is a language. You're describing what you want using some structure in a file, and you're giving it to a browser which is rendering it. It's a language. And you're programming, right? You're writing code, so it is a programming language, but it's not Turing complete. You can't do cycles and if statements and write things and add things, remove and seek. You can't do that stuff with HTML. You can with C++. You can with JavaScript. You can with Perl and Python and all these other languages. So there are a class of languages that are known as Turing complete, which are your programming languages. And then there are sort of other languages that are not. CSS, HTML are just some examples. Cool? Okay. So if someone tells you, I know how to program, I know HTML, you understand. Okay. So some of the high-level languages that we discussed. Again, high-level languages, remember, are languages that are reasonably easy for us to understand, reasonably, if you've studied it a bit, that then eventually turn into zeros and ones. They get translated into or compiled into zeros and ones. JavaScript, C, C++, C#, Objective-C, Python, PHP, Perl, blah, 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 blah. Many of you have heard of these languages. Now you understand kind of where they fit in computer science, in computing in general. Yes? Okay, so if you hear JavaScript, PHP, blah, you kind of know what that is. It's just a language that eventually turns into zeros and ones, and you get computation. Yeah, okay. Am I going too fast? Okay. Okay, when writing programs, complexity is the enemy. Consider the video games that you've played, or the operating system you've used, the tools you've used, the, social networks you've been on. Nobody sits there and just builds that. No one sits there and builds Facebook or builds an operating system or builds anything big. Instead, what they do is they build pieces, small pieces, pieces that they can understand, okay? Little bit at a time. Then they use those pieces as building blocks to build the next layer over the top. Think of it like Legos, right? Lego pieces. So you can build like a little piece with Legos, a bunch of them, and then you can use that as one big Lego block to build something bigger. And then you can use that as a big Lego block to build something bigger. And so in this way, you begin with something very simple. And as you build up, as you build layer upon layer upon layer, you're building up complexity. So you don't begin with complexity. You create complexity. Complexity emerges from simple pieces, from simple building blocks. This is why, I mean, imagine if something breaks on Windows, like there's a bug on Windows. Like no one is going to try to understand the entire system. That's just crazy. It's no one person can understand all, God knows how many, 5 million lines of code or however many it is. Nobody can do that. So instead what they do is they look at individual modules. They test them separately, they combine them, they see which one is misbehaving, they drill that, and they only look at that. They don't try to understand the entire thing because it's just too hard. It's too complex. So as programmers, one of the things that we absolutely have to do is try to componentize our programs, componentize the parts of our system, and keep them separate from the rest. Just like the engine is kept away from you when you're driving. Driving is complicated as is, right? You have people coming, there's like a ball going, a kid might come after it. Oh my God, it's a red light, no way to just turn green. All of that, imagine you also have to worry about the engine. It's too much. So the engine is abstracted away, you just get a wheel and the pedal, and you focus on driving, not the engine. Systems are built exactly this way. They abstract away the complexity so you can focus on what you're doing. Got it? Cool. Okay, Git. We'll be using Git quite a bit in this class. Let me just say what it is. Git is it's a program that allows engineers or programmers to share their code. Okay? It allows you to merge your code. So for example, suppose we're working on the same file. So I edited a little bit and you edited a little bit. How do we share it? How do I give you my changes or you give me your changes? Right? One thing we could do is literally take the file and email it. But suppose we have another team member. Well, they also edited. Who edited first? Who edited last? Which parts changed? It becomes kind of a mess, right? And also, if something breaks, we want to be able to go back. So we want some sort of a versioning system, right? So that we can roll changes back if we break something. All of that kind of management is done using a system or a program called Git. It's a very powerful tool. It's used in industry everywhere. And we'll be using it here to actually submit our programs. We'll be using Git. Now there is a website called GitHub. GitHub is not the same as Git. Git is just a program that allows you to do the various things I mentioned. It allows you to manage your code. GitHub is a website that hosts Git. So you can use, just like you can share with your friends, you can also share your code with GitHub. But the nice thing about GitHub is there's a lot of code there that's free and open source. So other people can then come and take your code and use it as well. They can also contribute to it if you give them the right access. So all of our code that we write, we'll be using Git and pushing it or sending it to GitHub. Right? So your next assignment, when you guys start writing code, you're going to push your assignment to GitHub. Right? And then in Moodle, you're going to give us the URL or the hyperlink, the reference, to your GitHub project. Cool. Questions so far? All right. Let's see. Should I talk about the internet? So no, I'm going to skip that part because we're going to talk about the internet later. There's going to be a whole class where we talk about IP, HTTP, blah, blah, blah. But I do want to talk about this. So let me zoom in just a little bit. So many of you might know this. Oh, I can't zoom. Wait. Oh, I can zoom. All right. OK. Can you guys read that? OK. So many of you have written things in here. It's important that you understand what that stuff is. OK? The first part, this part, is the protocol. What is a protocol? Anytime you hear protocol, it just means rule, okay? For example, I'm speaking English because I know you understand English. And we agree that the word yes means, and the word no means, right? It's an agreement between us, right? That's a protocol, right? It's an agreement that we're both going to understand the same thing, right? It's a standard. So in this case, this is saying use this protocol to communicate with something, some other computer. And we'll talk about what that is later. This is an address, right? In this case, we're communicating with a computer that has the name google.com. Now, in reality, this thing actually gets translated into a number using this thing called DNS. Don't worry about that for now. Just imagine this is the name of that other computer we want to talk to. Anyone know what this is? What is a port?
That's when it connects to a certain piece of the computer.
Okay, yes. Okay, so think of it this way. On your computer, you have different applications, right? So you might have Skype, you might have, I don't know, you might have Facebook running, you might have Messenger, you might have all these different things, right? And all of them are potentially communicating with other systems. Well, when your computer receives information, how does it know which program to give the information to? The way it knows is by this number. So what happens is when you want to communicate with the outside world, you reserve a port. A port literally means like, imagine you have like boats coming in. There's a port, right? So boats can come in different positions. So you reserve a port. You say, this is my port. Any information that comes to that port, give it to me. If that port is used, it gives an error, and I have to pick a different port, okay? So I'm Skype. I'm saying any messages that come to this port, send them to me. I'm Facebook Messenger. Any messages that come, send them to me. So this says the computer, this says the specific port, in other words, the program that will receive this information that I'm sending. With me? Okay? This right here is a path. Actually, anything past the port is just information that the receiver is getting, and then they can decide to do whatever they want. This is typically referred to as path. These are arguments. I don't want to discuss those. It's just additional information that you're sending to whoever is listening to this port on that computer using this mechanism, this protocol. Yes? Keep going? Questions? Wow, okay. Either you guys understand everything, which is great, or not. All right. So typically, people don't ask questions for two reasons, right? Either they understand nothing or they understand everything. I'm hoping it's the, okay. Server. What time is it? Oh, we have time. Okay. Sorry, when I get excited, I lose track of. If it's 2:45, tell me. Okay. So otherwise, I might keep going. What is a server? A server is just a computer. It's just a computer which has an address. Like, google.com has an address. Again, remember that address actually is a number. It's not really text, but it's an address, okay? And then you have your clients. Now, your clients are the things that you use all the time, like your phones or your computers, right? Your laptops, your whatever. These are your clients. When you log on to facebook.com, what's happening is a request, a packet, a message, if you will, is being sent from your device, from your phone, out through the web to a server, a computer, that has a specific address that this application is referring to. So you get to that, and remember that in the URL, in addition to the address, we can pass additional information, like the path, arguments, etc. So all that stuff goes to the server. The server is, again, a computer that has programs running on it. Remember, programs reserve port numbers, right? Now, suppose you make a request that goes to a program, let's say running on port number 80, okay? That's typically what servers run on, HTTP servers. It gets a request. It tries to understand, what do you want from me? Maybe what you want is a login page. And so it goes, OK, and it sends it back, and you get a login page. Then you type in your username and password, you hit submit, it makes another request. It sends another message to the server saying, hey, the user tried to log in, here's that information. It then looks at it, maybe looks up the username and password in a database, perhaps, to try to see, is this user actually registered with Facebook? And if they are, then maybe sends back their profile, right? If not, maybe it sends back an error saying, hey, invalid username and password, logging again. So this is what we call a client-server architecture. So the word architecture, you guys are familiar with like buildings, right? So an architect is the one that designs how the building is going to fit together and look and feel. Well, it turns out you can do the same with software, with programs, with systems. It's the same idea. You're trying to understand how things fit together. In this example, we have a computer that fits with this computer using a protocol, specifically HTTP. Okay? So in this architecture, we have a server, which is the thing that receives the request and sends back the response, and the clients, which are your devices that you're using to send requests. Okay? Gelucht bij tomater. Okay? Okay. We're not going to learn HTML because I want you to just go learn it. But just very quickly, okay? HTML basically looks like this. Remember, data is stored on files, right? So HTML is also data, which is a bunch of bits that's stored in a file. Yes? Okay. It has a name. I can give it whatever name I want, dot, and then the extension, that stuff at the end, the .txt, .doc, .jpg, that determines the kind of file that it is. Why do we have that extension? So that when you double click on it, Windows, for example, knows what application to use to open it. That's why you have that JPG or whatever. Well, one example. It gives us a hint of what's in there. Is it a picture? Is it code? What is it? HTML also has an extension. The extension is HTML. So if you ever see a file .html, it's an HTML file. And when you double click on it, you'll most likely get a browser because browsers know how to draw HTML. Make sense? Okay. So what does HTML have inside? Well, it has these things that are elements. We call them elements, okay? And you can nest an element inside another. So you can have underneath this, you can have this one, and that you can have that one. And elements, there are different elements. I don't expect you to memorize all of them, by the way, but there are some common ones that you should just know, like div, span, what a body is, head is, just memorize. It's like 10 different things. Just sit there, memorize it, you need it anyway. Style means the stuff inside is going to specify the look and feel of what you're going to see. So in this case, it's saying the tag that looks like this, H1, that would be this guy, have the text color be red. So anything inside of that H1, all of this stuff, is going to have red text.
There isn't a semicolon.
There's a what?
Besides the red.
Okay, you don't need it. If it's the last one, you don't need it. It's optional. You only need it if you have ones before that. Not bad, though. Okay, so in this case, so we have Tom rocks. This should say Tom rocks. I'll tell you why it's not later. And notice that it's red. Cool. By the way, what is HTML? It's basically just stuff that tells the browser how to draw something. Okay? So the browser literally reads this. It typically starts here to draw things. So it's saying, okay, in H1, which is like a block, inside of that I have Tom and rocks. I'm going to draw that. Then because it's a block, I'm going to go to the next line. And I'm going to draw IMG. That's probably an image. And look, there's a reference, a link to a picture. It's going to go download the picture, go to the server, get the picture, and then draw it on itself. And so you get Tom rocks and then the picture. But notice it doesn't say Tom, it says Tumanyan. Why? Here we have another tag, script. A script tag allows you to write JavaScript inside of your HTML. Moving forward, this is until we get to Node, which is later. For now, all of your assignments, when you write JavaScript, you will test inside of an HTML file. So you will typically store your JavaScript in a separate file. I'll show you how to do this. And then refer to it, just like image refers to an external file, an external JPG. Similarly, from script, you can refer to a separate JavaScript. In this case, I wrote the JavaScript directly inside the script tag, and let's see what it's doing. Document refers to this whole thing, right? The big thing. Inside the document, I'm calling this thing, function. If you don't know, don't worry. It's saying, get me the thing that has an ID of name. What has an ID with name in it? That guy, right? This element has an ID with name right there, right? There it is. So it's getting this element here. And then I'm saying inner HTML, make the HTML that is inside of it that. Tumanyan. So what's happening? This Tom is getting replaced with that stuff, with Tumanyan. And so the result of that is Tumanyan rocks, not Tom rocks. And that's a browser. And that's the address that you can write. It goes to the server. It makes the request. It pulls down this HTML. And then it draws the HTML in itself. Simple? Yes?
And if there were other names with the same ID name called,
illegal.
Also be renamed by somebody.
OK, so you're not supposed to. So IDs are meant to be unique.
Yeah.
What would happen? I'm assuming it depends. I don't know. Just don't do it. What would happen if I walk in front of a bus? It depends. If the guy stops, you'll be OK. In other words, if the browser just is nice to you, maybe it will do what you think you want to do, which is it will go through all the IDs and make them inner HTML. Maybe. Or maybe it will just take the first one. Actually, it probably does that one. Don't guess. Just do it right. Don't do that. OK. Good. Other questions? OK. So typically, when the question is, what happens if I make a mistake? The answer is, don't make a mistake. OK. All right. So we understand the basics of HTML, right? The very basic. You guys still have to go through Code Academy and learn the rest, but you got it. OK. Now, so we understood this part, which is that you have your application. It talks to a server. The server then sends you back results, something, information. It might be files. It might be pictures, whatever. It turns out, though, that the server can then use a database to store information and to retrieve information. So for example, if I'm on Facebook and I want to know who are my friends, a request can go to the server saying, give me Ruben's friends. It then does a query, possibly an SQL query, to a database, potentially MySQL, which will then return the list of people that I know, and then it returns back, draws the list of people that I know. So a database very often works together with a server. By the way, the database can either be on the same computer, but it can actually be on a separate computer. It doesn't have to be on the same one. With me so far? OK. OK, suppose you're actually Facebook. You're getting so many requests. It's not just one computer or phone that's sending in requests, like send me this person's profile, like, all that crap. It's not just one. It's lots, thousands, maybe even millions, right? Imagine all of those requests hitting a computer, one computer. That computer would have smoke coming out of it, right? I mean, there's no way you can possibly do that much computation that quickly. You can't keep up. So what can you do? What kind of scaling, what kind of methods of scaling did we discuss? Do you remember? Horizontal and vertical, exactly. So one thing you can do is make this computer just stronger, right? Add more memory, add more processors, just, okay? That's vertical scaling. But another thing you can do is add more computers. And what you do is when the request comes to this computer, it doesn't try to serve it. It doesn't try to compute. It just sends it to another computer. And then when the next request comes, it sends it to this guy, then this guy, then this guy, then that guy, that guy, that guy, that guy, that guy. And in this way, it's distributing the load across multiple computers. It's balancing the load. Balançando. It's balancing the load. This is known as a load balancer. It's just a computer. It's effectively a program that takes requests and sends them, routes them to other computers to actually do the computation. Did that make sense? Yay. OK. we talked about cloud services in the previous class. So cloud services provided by, Amazon has it, IBM, Google has it, there are other providers. They will host these computers for you. So instead of literally having this computer sitting in your room, like, keeping it cool, provisioning it, backing it up, whatever, doing all the work, you can just have these guys do it for you, right? So you just, literally, they give you access to a computer that in their server farm, and you just control it, you install what you want on it, blah, 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 and you run it. And they take care of the rest. They take care of cooling it, they take care of power outages, they take care of all of that. You just use their computers, and you just pay them for it, like you're renting a computer. Cool? All right. Okay. Typically, when we're talking about systems, specifically the client-server architecture, for database, when you're talking about databases, these are like the common databases that you see now, right? The really common ones. It's good to know them so that if people ask you, you kind of understand what they are and where they sit. What kind of database is that? Relational, thank you. What kind of database is that? No SQL. Anyone remember this one? Graph database, exactly. That one? Yeah, if it's got the word SQL in it, it's a relational database. That's a simple way to remember it. Okay, cool. So you have your database, which is the part that stores your data. You have your server, which is the thing that's getting information, getting requests and sending the response, right? Common servers include Apache, Microsoft IIS, Node, which we'll be using later, Nginx, and you can also do Tomcat for Java stuff. So if you see these guys, you kind of know that this is roughly where they are, right there on the server. Typically, again, on the client, you guys know this, I'm sure, is you have your browsers, usually. You can also have native applications on your computer that talk to a server, but typically you're using a browser, right? So you have your Chrome, Firefox, blah, blah, you know that. And then you have your operating systems for your phones. Cool? Okay, no problem. Programming languages. Now, a programming language on its own is just a language to communicate with a computer. But it turns out that typically languages have kind of fallen into certain places. Like you don't typically use PHP to write client-side applications. I'm sure someone could theoretically do it if they write enough other code, but it's not done, right? So typically, for your databases, you have SQL, which we studied, right? Structured query language to talk to the database. You can have other languages to communicate with the database. Like GraphQL, there's Sparkle, there's MapReduce, etc. These are languages that you typically communicate with a database with, the thing that stores your data. These here are the languages that you typically find on the server. Again, these are not absolutes, just generalities. So typically, if you see PHP, Python, Ruby, JavaScript is both, whatever. If you see .NET and Java, typically these guys sit on the server end, typically. And then on the client side, if you have a phone, if you have iOS, you're usually using Swift or Objective-C. Swift is kind of like a JavaScript-looking thing. It's like the new language for iOS. You can also use JavaScript. We'll talk about that later. For your computer, again, if you're just running in the browser, it's JavaScript, but you can also use it in tablets. And you have Java for if you're using, help me, Android. Thank you. So if you're programming Android, it's probably Java. If you're programming iOS, it's probably Objective-C or Swift. And everything else is basically JavaScript. Seriously, it's taking over, and you guys will enjoy that. Yeah, so far so good? Good. Okay, inside the browser, we have lots of code written by other people to help us write better code, okay? So a library, for example, is code written by someone else that we can use. It has an API. What's an API? Application Programming Interface. Some mechanism by which when I write my code, I can talk to the library. The interface, the medium through which I can communicate with the library, okay? There are also frameworks, which a lot of people don't quite understand the difference. One simple way that I'd like to think about it is that with a library, when you're writing your code, you call the library, do something for me. It does it, returns, and you keep writing your code. Okay? So you're controlling your code, the main structure of your code, but you're calling into the library to do something for you, some utility or whatever. With a framework, it's the other way around. The framework generally runs the application, the main structure, but then calls your code to do something when it decides. There are trade-offs to this, of course. The advantage is that there's a lot of code that the framework will just do for you, a lot of logic that you get for free, basically. The trade-off, though, the opposite, is that if it does something you don't want, that's kind of a problem, right? And then you end up what's known as fighting with the framework. You try to modify it, hack it, and okay. So really understand what framework you want to use, what it does and what it does not do before you use it. Because later on in the project, if it doesn't do what you want, you're going to have a problem. You're going to have to go and write the whole thing again, which sucks. Okay, so these are typical frameworks. Angular, maybe you guys have heard of it, and Ember are like the really popular frameworks now. As far as libraries, React and Vue are the popular rendering libraries. Again, remember, a library is something you call to do something. React is that. You call it, you say, draw this here, and it does a render, literally. And it draws something in the HTML. Vue.js is kind of similar, but it has some tweaks. Other libraries, whatever. I don't need to go into them. But basically, just familiarize yourself with this general category so that when you see it, you know, okay, that's the stuff people use to write web applications. Okay? Cool. Okay. It turns out that a lot of these things that we talked about come in groups, right? So, for example, you will often hear mean stack. What do you program? I call programming mean. The heck is mean? Mean basically means that for the database, they use Mongo. They use Express and Node for the server part, and they use Angular for the client part. If you remember, Express we didn't talk about because it's a framework for Node, don't worry. But this one, remember, that was in the database side. This one was in the server side, and this one was in the client side. Remember that? You can do a similar thing, except instead of Angular, you can use React. This is getting very popular now. This used to, actually, Zuckerberg wrote Facebook using this one, LAMP. So LAMP is Linux, so for the operating system, you use Linux. On the server, you run the Apache server on it. You run PHP as your server-side scripting language, MySQL for the database, and then, wait, he didn't use Python. Forget Python. Oh, this is like, you can do this or that. He used this one. He used PHP. You can also use Python. This is also very popular now. Cool? Okay. Okay, just one quick word about security. I find that when engineers first start programming, they know very little about security. And what they do is they write code the way their intuition tells them they should write code. The problem, though, is that a lot of the intuitions that you have about writing proper code are actually insecure. They're wrong. To write good code, you have to do some things that are actually not intuitive. And you have to explicitly know about it to not do it. So the only piece of advice I can give you for now is this. Before you start writing production-grade code, just read up on writing the kind of code that you're writing. So if you're writing server code where you're dealing with, let's say, a database, and you're writing queries, read up on mistakes, security mistakes you can make when writing queries. By the way, what's a security? I'm just curious if you know. A mistake you can make when writing a query on the server. Anyone know this? You guys?
Safe password.
What do you mean? Okay. No, SQL injection. Quote?
Yeah, if
Yeah?
you use a quote within from the password, it destroys the query, so then it gives you access to the first password.
Interesting. Okay, so you can try to break using, okay.
It's like SQL injection.
Right. It's similar, right. You're modifying the query. Yeah. So either you can just modify the query and have it run the way you want. Okay, most of you are looking at with blank faces. You don't know, no problem. Before you start writing queries, on a production grade application, read on how to write proper secure queries for applications. Otherwise, you're going to be in trouble. Eventually, you will get hacked. Actually, most of you are going to get hacked anyway, but at least minimize the probability. Okay. Okay, that's the word. Do we have time? 2 minutes for machine learning. Okay. So artificial intelligence is like getting really popular now. And it's getting really popular basically for 2 reasons. One is that we have an incredible amount of data now, just massive amounts of data. And the second is that the hardware has gotten much better. We have processors now that are really, really good and can process and compute very well. And machine learning, I would say, is like the really, really popular branch of artificial intelligence. And let me explain what I mean by that. So machine learning is, again, kind of a larger group, but within that, we have this notion of supervised learning. And what do I mean by this? Well, imagine you have like a magic box, and you have lots of data that has inputs and the expected outputs. So for example, suppose I said 1 and 1 as the inputs, and the output is 2. And then I said 5 and 5 is the input, and the output is 10. 9 and 1 is the input, and the output is 10, etc., etc. What might you think I'm trying to do? Addition, right? Okay, so this magic thing, basically when you feed the data properly and you train it, it will basically try to figure out what you're trying to do. It will magically figure out that what you're trying to do is add. And in the future, when you give it 100 and 100, it will try to guess that what you meant was 200. So what are the kinds of applications that are done? Well, for example, you give it as input email, and it tells you, is this spam or not? Gmail uses this kind of thing extensively, right? So they have lots of emails, and they know which ones are junk or not because you marked them as junk. So they have a big database of email to junk. And they have the rest of the emails that they assume are not junk. So they train these abstract magic boxes, which we'll talk about in a moment, to basically begin to make these predictions so that later when you give it another email that they have not seen before, this magic box tries to guess based on previous information whether this is junk or not, whether it's spam or not. Right? So typically you have, with supervised learning, you have these sort of mappings, this sort of input to output mappings. The input might be audio, and the output might be the text inside the audio. Like what is the person saying, the actual text. The input might be an image, and you're trying to figure out what is the object inside the image. Is it a dog? Is it a house? The input might be a language. It might be English, and the output, Spanish. Right? Input to output. It's trying to translate from A to B. Okay, so this thing is usually done through using something called a neural network. So we don't have a lot of time. I'll just so you guys get an idea. A neural network is basically, you have your input, and you have some sort of a mathematical function. And the mathematical function has an output. So in this case, for example, this is price versus size of the house. So generally speaking, you see that as the size of the house gets bigger, the price of the house also gets bigger, right? So we need to determine some sort of a mathematical function to fit this kind of data so that later, if we find a house that has a certain size, we can give that size and figure out roughly how much that house costs, okay? Okay, so one of these mathematical functions is called a neuron. Just bear with me. Now, just knowing the size of the house might not be enough. What if we want to know more information, like the number of bedrooms the house has, the zip code, that is to say the area in which the house is, average income of the people living in a house, assuming you have that kind of a statistic, right? Each one of these things can be one of those mathematical functions, one of those neurons, that then have an output that can be eventually fed into your output neuron that gives you a price. And in this way, what you can do is begin to chain things together. What you do is you have, for example, let's say you want to do image detection, right? So there's a camera and you want to know who's coming in and out of the building. When you take a picture of a person, you first run it through a set of neurons that attempt to find little shapes. You then take those shapes and feed them into another set of neurons that, based on those shapes, attempt to figure out parts of the face, the nose, the eyes, etc. You can then take the eyes and the nose and so on, feed it into another one that has been trained against that data to figure out faces. And then those faces can be matched against the database, and now you know who's going in and out of your building. Okay? Now, I did some hand waving. There's a lot of sort of math that I did not talk about. There are a lot of sort of back propagation and methods of how you eventually get the neural net to behave this way. Training, if you will. How do you eventually train this net to give you the right output, to fit the curve? There's quite a bit of that, and maybe once you guys are done with Intro to Comp Sci and you guys know a bit more math and you are able to program, you can begin to dive into this stuff, and it's really, really interesting. And I recommend that you guys start reading up on this. Right, so what do you need in order to do machine learning? You need math. By the way, people say you don't need math to program. It depends on what you're programming. If you're just building a website, true. But if you're building something like this, it's all math, it's all functions, so you need math. And typically, the language of choice for machine learning is Python. And Python, by the way, is not too dissimilar to JavaScript. So once you guys learn JavaScript here, you can then learn Python very easily. Okay, so there's, as you can imagine, and as you got from today's talk, there's a lot more. Computer science is awesome. And one of the things that makes it awesome is that no matter how much you know, there's still so much more you need to know. And new things are constantly coming out, new technologies, new concepts. You constantly have to read, you constantly have to learn. So welcome to the world of computer science, and I'll see you on Tuesday. Thank you. Faraz? Hartsook of Karen! Hey! John, merci, bravo.